So, let me kind of explain some of these questions. When you get to question number 1, Suave Bronco, so how that name came to be in this problem.
What?
Many, many years ago, a kid was reading a book and the character was named Suave Bronco. And he goes, Burkamp, here's your challenge. Work Suave Bronco into a problem. And so that's how Suave Bronco got into problem number 1. When you get to question number 4, so visualize this. So here's this bowstring, and you're going to pull back like this. So Monday, this will make sense why I have to use the word average. So what I'm saying is that when you pull that bowstring back, the average amount of force that you have to exert is 201 newtons.
Oh, because it's that.
Okay, because in reality it
You're pulling
changes.
on one point.
The farther you pull it, the harder it is because it follows Hooke's law. Okay? So when you draw that graph and that force distance graph on number 4, do not make this difficult. Here's the force distance graph. Draw a line at 201. Do not start it at 0 and go up to 201. Draw it as a horizontal line. Now, let's play name that shape, which gets you a
Rectangle.
which is why force times distance gets you work. Okay? Now, so on B, it says, with assuming no frictional loss of velocity, does the arrow leave the bow? So here's the story. So you've pulled this thing down. At this point, what have you stored?
Potential energy.
Potential energy. What's going to happen to all that potential energy?
It's going to change into kinetic.
Change into kinetic energy. Work done equals the change in the kinetic energy. Kinetic energy equals 1/2
MV
mv
squared.
squared. So the area underneath this graph is going to be your work, which is going to be your change in the kinetic energy. Then, it says, if the arrow is shot straight up, how high does the arrow rise? Well, if you know how much work it was done, which you do,
Then you know how much kinetic energy it has.
then you're going to know how much,
It will have
and then you can figure out,
height.
okay? Just saying. So when you get to number 5, ball is throwing downward. Keep in mind it's throwing downward, okay? It's throwing downward. Keep that in mind. So when it lands, what does it have to be doing? Faster or slower than when you threw it? Faster. So you know your velocity has to be a bigger number than when you threw it.
You throw it downward at constant
When you
velocity.
get to number 6, I was nice. I gave you the net upward force acting on the rocket. Okay? You don't have to subtract out the weight of the rocket. And the reason that we use net force on a rocket problem, because if here's Robbie the rocket, and if the upward force is less than the gravitational force, it's not going to go anywhere anyway.
It just sits there.
Yeah, it's just going to sit there, and there will be no change. So this is why you have to use the net force, okay? So in your calculations, you have the net force. Now, let me make a little note of what's going to happen when you get to these problems on page 311 and 312. Down there at the bottom, you have this little asterisk. Okay, so let me explain a little bit of geometry on this one. So when you get to question 28, so a wrecking ball is suspended from a 5-meter long cable, makes a 30-degree angle with the vertical. So here's where this equation becomes part of this story. So when something swings up in an arc length like this, to calculate the UG, you need the height, okay? But it's on an arc. So what this gives you, H equals L times minus L times cosine theta. Sometimes you'll see this written as L times 1 minus cosine theta. If you want to factor out an L, it's a personal preference thing. But here's the main part of the story. What this gives you is the vertical displacement. So if you remember yesterday, like when I swung that mass up, it's on an arc length. So this is why you have this equation. So that's what you're going to use to calculate the height. You need that for question 28, and then also problem 20. So that's why that is there.
Because it'll have the same amount of kinetic energy at the base as if it had just fallen from that height.
Exactly, because it's independent of the path.
Potential
Looks like the
energy
bottom,
from gravity.
all the kinetic.
Gravitation.
Yeah, so whether it falls like this or it swings in an arc, as long as that height is the same, because kinetic energy is a scalar quantity. So it's either kinetic energy going straight down or it's horizontal kinetic energy. Okay? Cool.
Cool.
Got it?
Yep.
Grand? Call it a weekend.